This is Heliox, where evidence meets empathy. Independent, moderated, timely, deep, gentle, clinical, global, and community conversations about things that matter. Breathe easy, we go deep and lightly surface the big ideas.
Imagine, if you will, being completely, utterly, and just hopelessly stuck.
Oh yeah, the worst feeling.
Right. Like you are in the driver's seat of your car. You're on the highway. But, well, it's not really a highway anymore. It's just a parking lot.
Just a sea of brake lights.
Exactly. There are cars, inches from your front bumper. Cars inches from your rear bumper. You're completely boxed in on the left and the right.
You can't inch forward even a little bit.
No, you can't reverse. You definitely can't change lanes. The entire system of moving vehicles has suddenly, almost magically, locked into this state of just absolute rigidity.
It's a total freeze.
Yeah. Or, think about the last time you moved apartments.
Yeah.
You've got this one rigid cardboard box, left, right, and a pile of random, completely odd-shaped items.
Oh, the dreaded final box. Always a nightmare.
Always. And you keep tossing them in, shaking the box, trying to get them to settle down.
Hoping they'll just magically fit.
Right. And at first, they kind of jiggle around. They find little pockets of space. But then you toss in that one final, seemingly insignificant item.
Like a tape dispenser or something.
Yes, exactly. A tape dispenser. And suddenly, nothing in the box can move. The whole structure is just locked. It is entirely frozen.
It's a very visceral feeling, honestly, that sudden, complete loss of freedom.
It really is.
And what's fascinating here is that this very physical, very frustrating state of being unable to move, well, it isn't just an annoyance of daily life. It is actually a massive, highly complex, and deeply scrutinized area of study in the world of physics.
Which is kind of wild to think about.
It is. It's a phenomenon known quite appropriately as jamming.
Jamming, like a traffic jam.
Exactly like that. And the reason we are looking at this today, the reason for this deep dive, is because of a brand new, frankly, landmark paper by Giorgio Parisi and Francesco Zamponi.
And these guys are heavy hitters.
Oh, absolutely. And they didn't just write, another incremental paper on jamming. They actually solved a decade-old mathematical mystery about how this transition works at the most fundamental, universal level.
And the thing that makes this paper truly historic, in my opinion, is how they actually solved it.
Yeah, this is the best part.
Because they didn't crack this mathematical white whale entirely on their own, did they?
No, they didn't.
They had a major assist from an AI chatbot.
Yep. Essentially
a large language model, which derived the highly complex mathematical proof almost entirely by itself.
Which is just, it's mind-blowing.
It really is. To use a rough analogy, it's like, okay, imagine having two incredibly detailed maps of the exact same sprawling city.
Okay, I'm picturing it.
One map was drawn by geographers who were actually looking at the physical streets, and the other map was drawn by mathematicians calculating abstract geometry in infinite dimensions.
Right, two completely different approaches.
Exactly. And for 10 years, the smartest people on Earth suspected these two maps were showing the exact city. But they couldn't figure out how to fold the paper to make the streets line up perfectly.
They just couldn't find the physical link.
Right. Until an AI comes along, looks at the maps, makes a few crisp folds, and just says, here you go, they match.
That framing gets right to the heart of the breakthrough, I think, because we are dealing with an evolving meta-story here.
A meta-story? How so?
Well, it's about how the very nature of scientific discovery is being fundamentally altered.
Oh, I see what you mean.
Yeah, the human geniuses had systematically overcomplicated this problem for 10 years.
Right, looking for elegance.
Exactly, looking for an elegant solution. While the AI, it just rolled up its sleeves and brute forced the messy algebra.
It just did the dirty work.
It really did. But to fully appreciate the magnitude of what the AI actually did, we have to understand what it means to be jammed in the first place.
Right. Let's ground this in the physical world first. Because when we talk about jamming in physics, we aren't actually talking about cars on a highway, right?
No, not at all.
We're talking about granular matter.
Yeah.
So what are the physicists actually studying when they look at this?
To understand jamming, you have to picture what physicists call amorphous packings of hard or soft spheres.
Okay, amorphous packings.
Yeah. So strip away the complexity of cars with human drivers making, weird, unpredictable decisions.
No turn signals to worry about.
Right. Think of something simpler, structurally chaotic, and macroscopic.
Like what? Give me a visual.
Coffee beans in a grinder,
Oh, okay.
or sand on a beach, or even a massive industrial silo filled with grain.
So just lots of individual physical objects piled up.
Exactly. And these are macroscopic particles, meaning they don't have thermal motion the way microscopic molecules in a gas or a liquid do.
Wait, can you break that down? Thermal motion?
Sure. So unlike a glass of water where the H2O molecules are constantly vibrating and bouncing off each other.
Just naturally because of ambient temperature.
Right, precisely. A pile of coffee beans is just, well, it's dead inert.
Dead inert.
Yeah. If you
Okay.
don't touch them, they don't move, they don't jiggle on their own.
Okay, so they are entirely governed by geometry and external force, not temperature.
You nailed it. Now, when you start to compress these spheres, or when you pack them into a confined space and slowly increase the density.
Like pouring more beans into the grinder.
Exactly. Something really profound happens.
Okay.
At low densities, these spheres can easily slide past one another. The whole collection flows almost like a liquid.
Right. Think about pouring sand out of a bucket. It just flows.
It does. But as you increase the density, they get crowded, they start to touch.
And eventually,
Eventually, you reach a very specific critical density threshold. And at this exact point, the system undergoes a non-equilibrium transition.
a non-equilibrium transition. Okay, if you're listening and trying to picture that, think about how water freezing into ice is an equilibrium phase transition, right?
Right, that's driven by dropping the temperature.
But this jamming transition, it has nothing to do with temperature. It's driven purely by crowding.
Yes, it's a geometric lockup.
A geometric lockup, I like that.
Above the specific density, mechanical rigidity just suddenly sets in.
The beans get stuck.
Completely. The particles are locked into a contact network, they push against each other, forces are transmitted through the entire pile, and the whole amorphous, chaotic mess suddenly acts like a solid.
Like how you can stand on a tightly packed pile of sand without sinking.
Exactly.
Now-
That is the jamming transition.
Wow, okay.
And the reason physicists care so deeply about this is that granular materials are actually the second most manipulated substance in global industry.
Wait, really? The second most?
Right behind water.
That is wild. I had no idea.
Yeah. So understanding how a silo of grain suddenly jams and then violently unjams, well, that can prevent catastrophic industrial collapses.
Oh, sure. Or predict the mechanics of a deadly avalanche.
Exactly. It has massive real-world implications.
And reading through the source material, the paper notes that right near this specific transition point, that razor's edge where the coffee beans go from flowing to frozen.
Right on that boundary.
Yeah, right there, the physics gets incredibly weird, but also universal.
Mm.
The paper talks about observables showing, and I'm quoting here, power law critical behavior.
Ugh.
Ah, yes, power law critical behavior.
Which, translating out of physics speak, basically means that right at the edge of jamming, mathematical rules emerge that apply to almost any jammed system.
Regardless of what it's made of.
Right. Whether it's coffee beans, sand, or plastic beads.
That universality is actually the holy grail for theoretical physicists.
Yeah, is that?
Because when a system is right on the edge of jamming, just barely touching, just barely solid, it exists in this highly sensitive, extremely precarious state.
Like a house of cards.
Exactly like a house of cards.
Yeah.
And to describe this state, physicists use 3 specific physical measurements.
Okay. What are they?
They're governed by what they call critical exponents.
Mm-hmm.
These are essentially the mathematical rules of the road for how the system behaves as it approaches the jamming point.
Okay.
The paper highlights 3 of them in the physical world: alpha, theta, and kappa.
Alpha, theta, and kappa.
Right.
Let's break down what those Greek letters actually measure in the real world.
So if I'm, say, a tiny ant crawling inside this jammed pile of coffee beans, what is alpha actually telling me?
Okay, so alpha controls the gap distribution.
Gap distribution.
Yeah. As that ant, if you look around, you would measure the tiny microscopic distances between beans that are almost touching, but not quite.
The near misses.
Exactly. And as you get closer and closer to the exact jamming density, the radial distribution function diverges.
Wait, what does that mean in ant terms?
It basically means alpha tells you exactly how the number of these tiny near-miss gaps just explodes as the system locks up.
Oh, I see. So it's a measure of the negative space, the almost contacts.
Perfectly put, yes.
Okay, what about theta?
Theta controls the force distribution.
Force distribution.
Yeah.
So the actual physical pressure.
Right. Once the spheres are actually touching and jammed, they exert forces on each other to hold the whole structure up.
Oh, I see.
But Not all contacts carry the same weight. You have a few massive force chains carrying the bulk of the load.
Like the pillars of a building.
Right, and then you have a vast network of extremely weak contacts that are just barely grazing each other.
Okay, so where does theta come in?
Theta describes the probability of finding these incredibly weak, tiny forces within that network.
I see. So alpha measures the gaps, theta measures the weak forces.
Yeah.
What about the last one, kappa?
Kappa relates to the overlap distribution, sometimes called mean square displacement.
Overlap. You mean like the beans actually squishing into each other?
Exactly. If you have soft spheres, imagine rubber balls instead of hard coffee beans.
Okay, got it.
And you push them past the jamming point, they have to go somewhere, so they start to deform and overlap.
Oh, sure, they compress.
Right. Kappa tells you how that overlap behaves as the pressure scales up.
Okay, so measuring these three dials caps, weak forces and overlaps, that gives us a complete physical description of what it means to be jammed.
It gives us the whole picture.
But they aren't just random numbers, are they? The source points out that a researcher named Wiart and his collaborators made this massive breakthrough by proving these three dials are mechanically linked.
They are inextricably linked. And the concept Wiart used to prove this is really beautiful. It's called mechanical marginal stability.
Mechanical marginal stability. I want to dig into that term because it really seems to be the engine driving this entire physics problem.
It absolutely is.
So what does it actually mean for a pile of spheres to be marginally stable?
It means the physical network of forces holding the whole jammed structure together has exactly enough contacts to remain a solid, and not one contact more.
It's incredibly fragile.
It is on the absolute razor's edge of falling apart. To visualize it, don't think of a sturdy brick wall.
Okay.
Think of a highly complex suspension bridge that has been engineered to its absolute limit.
Oh, that's a great analogy.
Yeah, every single cable, every single wire is under maximum tension, contributing perfectly to the rigidity of the deck.
So there's no redundancy.
Zero redundancy.
Wow. So if you snip even one tiny wire,
The tension redistributes catastrophically. The deck ripples, the other cables snap, and the whole solid structure instantly devolves into fluid, chaotic motion.
it just collapses back into unjammed liquid.
Exactly. The system is structurally stable, but only marginally so.
Marginally stable, got it.
And because a jammed pile of spheres is in this incredibly precarious razor-edge state, Wiart was able to figure out the exact mathematical relationship between those three dials.
He found the master equation for the bridge.
He did. He derived specific scaling relations showing that alpha and kappa are entirely dictated by the weak forces, theta.
Wait, so theta is kind of the boss dial?
You could say that, yeah. Mathematically, he proved that alpha equals 1 divided by 2 plus theta,
Okay.
and kappa equals 2 minus 2 divided by 3 plus theta.
Which means the geographers have finished the map of the physical city.
Yes.
We know exactly how the streets of alpha, theta, and kappa connect, entirely because of the gravity of that suspension bridge, the mechanical marginal stability.
That is exactly right. But that is only half the story.
Of course it is.
Because while Wiart was looking at physical forces in 3 dimensions, another group of researchers was approaching this exact same traffic jam from a totally different dimension.
And this is where it gets a little sci-fi.
Quite literally infinite dimensions.
Infinite dimensions, okay?
Huh.
This is where the paper introduces the CKPUZ team.
Huh.
That's an acronym, right?
Yes. It stands for Charbonneau, Kirchan, Parisi, Urbani, and Zamponi.
2 of whom, Parisi and Zamponi, wrote the paper we are looking at today.
Correct.
So back in 2014, they created an exact mean field description of jamming. But they didn't do it by looking at 3D coffee beans or suspension bridges.
No, they do.
They calculated the physics of hard spheres in infinite dimensions. And I have to stop here, because if you're listening and wondering why anyone would care about an infinite dimensional sphere, you are not alone.
It's a very fair question.
My brain evolved to track 3 spatial dimensions entirely so I don't walk into a wall.
Right, our brains just aren't built for it.
So why are some of the smartest physicists in the world doing math in infinity? What's the point?
I know it sounds like a purely academic exercise, just math for the sake of math.
Yeah.
But it's actually a profound mathematical trick to strip away real-world noise.
Wait, really? A trick?
Yeah. You see, 3 dimensions are incredibly messy for physicists.
Messy how?
Well, in 3D, particles get tangled up in local geometric frustrations.
Local frustrations.
Yeah, they form little localized crystalline structures, tiny pyramids of spheres that just sort of muddy the overall math of the chaotic system.
Oh, I get it. The local geography gets in the way of seeing the global pattern. Like getting lost in a cul-de-sac when you're trying to see the layout of the whole city.
Precisely. But as you mathematically increase the number of dimensions,
4, 5, 10.
100
Bye.
infinity, the geometry actually becomes simpler.
Wait, more dimensions makes it simpler? That feels completely backwards.
It does, but it becomes what physicists call a mean field.
A mean field. Okay, explain that.
In infinite dimensions, every particle has so many neighbors that it essentially interacts with the average background of every other particle.
Oh, I see.
The localized crystalline messiness just averages out entirely. You are left with the pure, unadulterated, fundamental essence of the jamming transition.
Okay, that actually makes sense. So infinite dimensions isn't a complication at all. It's a distillation.
Exactly. It's a purification of the problem.
You boil away the 3D local traffic jams to see the absolute purest form of the traffic jam.
Yes.
But when the CKPUZ team looked at this infinite dimensional skeleton, they found something that just sounds incredibly daunting. The source calls it a property of the full replica symmetry breaking, or full RSB saddle point.
Yeah, it's a mouthful.
We cannot skip over this. What on earth is replica symmetry breaking? Are we talking about cloning universes here?
We aren't cloning universes, no, but we are mathematically cloning the system.
Mathematically cloning, okay.
Replica symmetry breaking is actually the concept that won Giorgio Parisi the Nobel Prize in physics.
Oh, wow. So this is his signature move.
It is. He originally developed it to understand spin glasses.
Spin glasses.
They are magnetic alloys where the magnetic atoms are arranged randomly. And because of that randomness, it leads to immense geometric frustration.
Geometric frustration. Just like our coffee beans are arranged randomly and get frustrated trying to pack together.
Exactly the same principle.
Wow.
So, to solve the math of this chaotic disorder, Parisi introduced the replica trick.
The replica trick. How does that work?
You imagine taking an identical copies or replicas of your disordered system.
Okay, in copies. Got it.
You let them all evolve, and you look at how these replicas overlap with each other. Now, if the system is simple, all the replicas end up looking the same.
Because there's an obvious best way for them to settle.
Right. And in that case, the symmetry is intact.
But what if the system is incredibly complex and frustrated, like a jammed pile of infinite dimensional spheres?
Then the replicas freeze into many different, vastly distinct configurations. They don't look the same anymore.
Wow.
The symmetry between the replicas is broken.
Hence, replica symmetry breaking.
Exactly. And what the CKPUZ team found was that in infinite dimensions, the jamming transition occurs at a specific, marginally stable point within this replica framework.
The full RSB saddle point.
You got it.
Okay, so let me summarize where we are. Wired had his physical suspension bridge, the mechanical marginal stability in 3D,
Right.
and the CKPZ team found an abstract, infinite dimensional mathematical suspension bridge, phase space, marginal stability.
Exactly.
And just like Wired had his physical dials, the alpha, theta, and kappa we talked about, the CKPUZ team derived their own set of critical exponents for their abstract world.
Right. They call them A, B, and C.
A, B, and C. Which brings us to the most important question in this entire field of physics.
The billion-dollar question.
Are these two maps showing the same city?
Yes. The holy grail was to prove that these two concepts of marginality, the physical suspension bridge of forces and the abstract mathematical replica symmetry breaking, are actually the exact same universal phenomenon.
And the key to bridging that massive gap, the key to proving that physical reality and abstract infinite math were singing the exact same song, all came down to one maddeningly simple equation.
The great mathematical white whale of the CKPUZ team.
The white whale. Let's trace this conflict because it really is a story of profound scientific frustration.
It really is.
So back in 2014, the CKPUZ team had their abstract exponents, A, B, and C. And they had actually figured out the translation manual to the physical exponents, hadn't they?
They had the dictionary.
Right. Look at the translation equations in the source text right now. They proved that physical alpha is equal to abstract A divided by B.
Okay.
Physical theta is equal to C minus A, all divided by B minus C.
Yep.
And physical kappa is equal to C plus 1.
Right, so they knew exactly how the abstract letters mapped to the physical letters.
But having the dictionary isn't the same as proving the languages are identical.
Exactly. To prove that this dictionary actually yielded Wiart's mechanical stability equations, they needed to prove one tiny, simple little internal relation between their own abstract exponents.
What was it?
They needed to prove that abstract exponent A plus abstract exponent B equals exactly 1.
A plus B equals 1. That's it.
That's it. If A plus B equals 1, The translation equations perfectly collapse into Wiart's equation.
Two maps fold together perfectly.
Yes, the phase-space marginality and the mechanical marginality become mathematically identical.
Okay, so in 2014, why couldn't they just prove a plus b equals 1? It sounds like kindergarten math.
Because they could only prove it numerically.
Numerically?
Yeah.
Meaning with a computer.
Right. The CKPUZ team used computers to calculate the values of A and B to an extraordinary degree of precision, and they found that A was roughly 0.29213,
Okay.
and B was roughly 0.70787.
And if I add 0.29213 to 0.70787, I get exactly 1.000000. It adds up perfectly.
To an arbitrary degree of numerical precision, yes, it adds up to 1.
So what's the problem?
Well, in theoretical physics, especially when dealing with infinite dimensions, numerical observation is never enough.
Really? Even if it's precise to like 100 decimal places?
Even then, computers are finite machines, you know? They rely on grids and rounding, they have limits. But an infinite dimensional theory requires an infinite dimensional mathematical guarantee.
Ah, I see.
A numerical result tells you that something is likely true, but an analytical, rigorous proof tells you why it is true.
Okay, so it's the difference between noticing that the sun rises every morning and actually understanding the orbital mechanics of the solar system.
That is a perfect way to put it.
Without the analytical proof showing the step-by-step algebra of how A and B interact, A plus B equals 1 is just a very, very convincing coincidence.
It's a conjecture, not a law.
It's like knowing the answer to the math test is 1 because you peeped at the teacher's answer key, but you get a 0 on the test because you can't show your work.
That is exactly what it felt like for them. And for a decade, from 2014 to 2024, some of the most brilliant minds in statistical mechanics threw themselves at this problem.
10 years of trying to show their work.
10 years. They needed to derive A plus B equals 1 strictly from the underlying full RSB scaling equations.
And those equations are not simple.
They are massive, nonlinear integral differential equations. They are monsters. And for 10 years, they found nothing but dead ends.
But wait, Giorgio Parisi is a Nobel laureate? He literally co-invented the replica symmetry-breaking framework.
He did.
If anyone on Earth could show their work to the math teacher, it should be him. Why couldn't human geniuses solve this?
The answer to that reveals a really profound bias in human cognition.
A bias? How so?
Well, human beings, even genius theoretical physicists, we have a very specific aesthetic when it comes to math.
We like things to look nice.
Exactly. We look for patterns. We look for elegance. We look for profound, deep symmetries. When a human looks at a problem that bridges two massive concepts of the universe, they expect the bridge itself to be beautiful.
They want a conceptual masterstroke that makes the math sing.
Right. They want the aha moment to feel profound.
But what if the bridge isn't beautiful? What if the bridge is just a tangled, ugly, brutally chaotic mess of algebraic cancellations?
Then the human brain gets fatigued.
We just give up.
Basically, a human physicist looks at a page-long fractal of expanding algebraic terms and thinks this is too messy, there is no conceptual insight here, I must have taken a wrong turn.
I must have messed up step 2. Let me start over.
Exactly. And they abandon that path to look for something more elegant.
So they didn't need a smarter human.
No, they didn't. They needed a completely different kind of intelligence, a mind that doesn't get tired. And a mind that doesn't care if the math is elegant or ugly.
Which brings us to the turning point of the paper. The humans realized their own limitations, and they called in an untiring algebraic engine.
Exactly. Parisi and Zamponi decided to feed this decade-old problem into an AI.
Wow.
Specifically, they used the Claude model. The paper mentions using both Sonnet 4.6 and Opus 4.7.
Okay, Claude. And the methodology here is crucial to understand, I think, because it dismantles this popular idea that AI is just a magic oracle.
Oh, absolutely. This wasn't magic.
Right. They didn't just open a chat window, type, prove A plus B equals 1, hit enter, and go grab a coffee.
Not at all.
The source text explicitly states this was a rigorous, collaborative process containing 40 distinct prompts.
40 prompts are real conversation.
So how do you even begin a conversation with an AI about an infinite dimensional physics problem? Where do you even start?
Well, you start by testing its competence. You have to know if it even understands what you're talking about.
Like an interview.
Exactly.
Yeah.
The first part of the conversation was incredibly grounded. The physicists actually had the AI study the differential equations numerically.
Okay.
They asked Claude to write a C++ program to find the solution and verify the conjecture to high precision.
That is fascinating. So the physicists already knew the numerical answer from 2014. They were basically giving the AI an entrance exam.
Exactly. They were saying, before we trust you with the white whale, let's see if you can even comprehend the specific, highly technical language of these full RSB scaling equations.
Can you speak our language?
Yes. They were establishing a baseline of mutual understanding and defining the strict boundaries of the physics.
And Claude passed the exam?
It did. It wrote the C++ code and correctly interpreted the numerical reality, and once it proved that, they began to push it toward the analytical proof.
The thing the humans couldn't do.
Right, and this is where the dynamic gets really interesting, because it was an iterative collaboration.
What did that back and forth actually look like? Did the AI make mistakes?
Oh, it definitely did. Large language models are notoriously prone to glossing over rigorous steps or making algebraic leaps that aren't fully justified.
Hallucinating math.
Right. In an early version of the proof, the AI made a logical leap. The physicists reviewed the output, found the inconsistency, and prompted the AI again, pointing out the specific flaw in its logic.
So it's literally like a brilliant but sloppy graduate student working at the whiteboard.
That is the perfect analogy.
The professor says, hold on, your logic in step 3 is flawed. You can't assume that variable cancels out.
Right. And the student looks at it, realizes the error, and recalculates a new path. That is the exact dynamic that happened here.
Wow.
When the physicist pointed out the inconsistency, the model corrected itself. It understood the error and fixed the algebraic path.
It learned.
It did. They even used a slightly faster model, Sonnet 4.6, to brainstorm and refine some of the minor intermediate steps before bringing the refined logic back to Opus 4.7 to write down the final, formal mathematical proof.
And the paper says, and I quote, the model Opus 4.7 essentially derived the proof by itself, with minimal supervision from us.
Yeah.
That sentence alone is a watershed moment in theoretical physics.
It really is, and they didn't hide it, which I love. Parisi and Zamponi deposited the full, unedited chat logs into a Zenodo repository for the entire world to see.
Which is fantastic for the scientific record, completely demystifies the process.
Exactly. It allows anyone to study exactly how the prompt engineering led to the breakthrough.
It proves that the AI wasn't generating new physics. It was executing complex logic within the rigid boundaries set by human intuition.
Right. The humans defined the phenomenon of jamming. The humans derived the initial infinitely dimensional theories, and the humans identified that A plus B equals 1 was the crucial missing link.
The AI didn't wake up one morning feeling curious about coffee beans.
No, it didn't have an epiphany.
It just acted as the ultimate algebraic bulldozer, perfectly willing to drive through the ugliest jungle of calculus imaginable.
That's a great way to describe it. A bulldozer.
So what exactly did this bulldozer uncover? How did it actually prove A plus B equals 1?
Well, to understand the proof, we don't need to read out the nonlinear differential equations. That would be terrible audio.
Yeah, please don't.
We just need to follow the narrative arc of the AI's logic, which is organized into 4 main steps.
Okay, let's go through them. Step 1, setting the game board.
Right. Step 1 involves revisiting a linear eigenvalue equation for a function they call P1.
T1.
Yeah. Essentially, the AI rewrote the fundamental physics equation into a specific format that equals exactly 0.
Okay, why make it equal 0?
Because the takeaway here is that once the equation equals 0, you can multiply it by any arbitrary differentiable test function, which they call XCI, spelled XI.
GD. Okay.
And you can integrate it, and the entire massive equation will still equal 0, because anything times 0 is 0.
Oh. It's like finding a universal slot machine.
How do you mean?
Like, if you can forge the exact perfect the perfect test function XCA, you can drop it into this equation and force the math to reveal its secrets, and the machine still balances out to 0.
That is exactly it. Which brings us to step 2, the critical aha moment of the entire proof.
This is the moment the AI did the thing the humans couldn't do.
Yes. The AI needed to build this magical coin, this test function 11.
What did it build it out of?
It decided to build it out of another function called f, which dictates the scaling of the overlaps between our infinite dimensional spheres.
Okay, so it used f.
And the AI defined the test function simply as a xi equals f times 1 minus f.
Xi equals f times 1 minus f.
Yep.
I mean, it looks innocent, it looks simple.
It looks very simple, but when you drop that specific coin into the massive eigenvalue equation and expand the algebra,
What happens?
it spawns a horrific page-long fractal of algebraic terms. It is an absolute nightmare of integrals and derivatives.
So this is the ugly jungle you mentioned earlier.
Yes, for a human physicist, this is the exact moment you give up. You look at this chaotic explosion of symbols, you see no conceptual elegance, and you assume you've made a mistake.
You throw away the paper and start over.
Exactly. But the AI doesn't feel fatigue.
It just kept crunching.
It just kept crunching. It expanded every single term. And it realized that buried inside this horrific mess, two incredibly complex, nasty algebraic groupings explicitly and perfectly canceled each other out.
Wait, so the ugly math just destroyed itself?
It did. And when the smoke cleared from that massive cancellation, the AI was left with a surprisingly clean algebraic identity.
Oh, wow.
It boiled down to an equation involving three specific integrals, which the paper labels k, n, and d.
Okay, k, n, and d. I'm looking at the source, and the identity the AI pulled out of the wreckage is c times the quantity d minus 2n equals the quantity 1 minus a minus b times k.
Keep that equation front and center.
Wow.
C times d minus 2n equals 1 minus a minus b times k.
I can literally see the a plus b sitting right there inside the parentheses. It's like seeing the shark's fin break the surface of the water.
We are incredibly close now. Now we move to step 3.
What's step 3?
This is where the physicists bring back a rule from their original 2014 paper.
Oh, a blast from the past.
Yeah. Way back then, as part of the marginal stability identity, they had already rigorously proven a relationship between those integrals d and n.
What was the relationship?
They proved that the integral d always equals 2 times the integral n, so d equals 2n.
Wait a second. If d equals 2n, then d minus 2n is just 0.
Exactly.
So if you plug that 0 into the AI's shiny new identity, the entire left side of the equation, this c times d minus 2n apart, it just vanishes. It becomes exactly 0.
Yes, it does.
So the massive infinite dimensional equation has now been reduced to 0 equals the quantity 1 minus a minus b times k.
Yes. And basic algebra tells us that if two things multiply together equals 0, then one of those things must be 0.
Right. Either the chunk 1 minus a minus b is 0.
Which would mean 1 minus a minus b equals 0, so 1 equals a plus b.
Which is exactly what we want to prove.
Right. OR.
Oh no, there's an or.
Or it means the integral k is 0.
The trapdoor.
Yeah. If k is 0, then the equation just reads 0 equals 0.
Which means we learn absolutely nothing about our exponents a and b.
Right. And the decade-old mystery remains totally unsolved.
Which means everything? The entire decade of human intuition, the 4D prompts with the AI, the massive algebraic cancellations, the entire bridge between physical suspension bridges and infinite dimensional replicas, it all comes down to proving one single thing.
Step 4.
The final boss.
Yeah.
We have to definitively prove that the integral k is not 0.
Exactly.
In fact, the source notes they needed to prove k is strictly greater than 0 to be absolutely safe. How do they possibly prove that?
This is where the story takes a wildly unexpected turn. It goes into a completely different scientific discipline.
Wait, really? What discipline?
To prove that k is greater than 0, the AI and the physicists didn't use a standard trick from statistical mechanics.
Okay.
They realized that their physics equation was structurally identical to a famous equation from biology.
Biology. We're talking about infinite dimensional hard spheres locking up into a solid, and we're going to use biology math.
Yes, we are. They use something called the Fisher-KPP equation.
Fisher-KPP, what is that?
It is a reaction diffusion equation. It was developed independently in 1937 by R.A. Fisher and a Soviet team of Kolmogorov, Petrovsky, and Piskunov.
That's the KPP.
Right. And it was originally designed to study population genetics, specifically what they called the wave of advantageous genes.
Let's unpack that, because I am lost.
Yeah.
How does this biological equation work in the real world? What is it modeling?
It models logistic growth combined with spatial diffusion.
Okay, give me a visual.
Imagine a population of rabbits introduced to a massive, empty, grassy field.
Okay, rabbits in a field. Got it.
The rabbits will multiply. That's the reaction, or the logistic growth part of the equation.
Because they're rabbits.
Right. But they won't just stay in one spot and pile up infinitely.
No, they'll spread out to eat more grass.
Exactly. They will spread out across the territory to find new grass. That is the diffusion part of the equation. The Fisher-KPP equation mathematically perfectly describes how that population wave spreads over space and time.
Okay, I can picture the wave of rabbits spreading across a map. But how does that math govern the actual limits of the growth?
Well, the logistic growth part of the equation ensures that the population fraction always stays between 0 and 1.
0, 1.
Meaning what? 0 means no rabbits, extinction.
Okay.
One means the field is at absolute maximum carrying capacity. There is literally no more grass to support even one single more rabbit.
So the math of the Fisher-KPP equation has a built-in limit.
Yes, it has a built-in what they call a parabolic maximum principle. It mathematically proves the population fraction can never dip below 0.
Because you can't have negative rabbits.
Right, you can't have negative rabbits, and it proves it can never exceed 1.
Because you can't have infinite rabbits in a finite field. Okay, the rabbit math makes perfect sense to me. But how on earth does an equation about rabbit population limits apply to the infinite dimensional math of jammed coffee beans? I don't see the connection.
The connection is that the underlying skeleton of the math is universal.
The skeleton is the same.
Yes. The AI and the physicists realized that the differential equation controlling their jamming function, that function F we used to build our magical test coin earlier,
Right.
that equation had the exact same mathematical structure as the Fisher-KPP equation.
You're kidding?
No. The variables represented completely different things physically, but the algebraic engine driving it was identical to logistic growth with diffusion. The jamming equation had that same 1 minus F structure that limits the growth of the rabbits.
That is mind-bending.
It really is.
It's like finding out the engine inside your sleek sports car is mathematically identical to the mechanism driving an old grandfather clock.
Yes.
It's just spinning different gears, but the math is identical.
That is a perfect analogy. And because the mathematical skeleton is identical, all the rigorous mathematical rules that apply to the biology equation
Also apply to the physics equation.
exactly. So by invoking the biological maximum principle, they definitively proved that their jamming function f must always stay strictly between 0 and 1.
It's bounded.
Yeah.
Just like you can't have negative rabbits, the jamming function f can never be negative, and it can never be greater than 1.
Exactly.
And why is that the silver bullet for our final boss, k? Why does that solve everything?
Because the integral k is defined mathematically as the integral of f times 1 minus f multiplied by a strictly positive probability function.
Okay, let me do the math in my head.
Go for it.
If we now know for an absolute fact that f is strictly between 0 and 1, then f is a positive number.
Yeah.
And 1 minus f is also a positive number.
Yes.
A positive times a positive is a positive.
Always.
Therefore, the entire integral k must be strictly, unequivocally greater than 0.
The final domino falls. K is positive. K is definitely not 0.
Wow. Let's trace this triumph all the way back up the chain, because this is so satisfying.
Let's do it.
We had our reduced identity from the AI. 0 equals 1 minus a minus b all times k.
Yes.
We just used 1930s rabbit math to prove that k is a positive number,
We did.
which means, algebraically, the only mathematical way that equation can possibly equal 0 is if the other chunk, the 1 minus a minus b, equals exactly 0.
Exactly. And if 1 minus a minus b equals 0,
You just move the a and the b to the other side of the equal sign, and you get 1 equals a plus b.
the proof is complete.
The decade-old mystery is solved.
It is officially solved. The bridge is built. By proving analytically that a plus b equals 1, Parisi, Zamponi, and Claude have formally proven that the infinite dimensional mathematical map and the 3D physical map are perfectly aligned.
To match up.
They match perfectly. The abstract phase-space marginality of the replica symmetry breaking and the real-world mechanical marginality of the suspension bridge. They coincide perfectly at the level of critical exponents.
They're two different languages describing the exact same universal truth of the jamming transition.
Exactly.
It's just breathtaking when you step back and look at the whole tapestry here.
It really is a masterpiece of logic.
I mean, we went from traffic jams and coffee beans to infinite dimensional cloned replicas to a collaborative dialogue with an artificial intelligence to the population dynamics of rabbits in a field, all colliding to solve a single addition problem.
A plus b equals 1.
It really is a triumph of interdisciplinary math and modern technology.
It is. But I think it's deeply important to reflect on the human element of this story.
The human element.
Yeah, because despite the AI doing the heavy lifting on the brute force algebra, the paper ends on a surprisingly human, vulnerable note from the authors themselves.
Yes, I noticed that in the discussion section of the source text.
Yeah.
It's incredibly rare to see this level of introspection in a dense physics paper.
Almost unheard of.
The authors actually ask themselves, right there on the page, why have we not seen the proof? They spent 10 years on this. Why didn't they find it? And the answer they give is a profound admission of human bias. They wrote, "We have not even tried to use this approach. We thought there was a deep, hidden, direct relationship between the functions that we were unable to see. We were looking for something deeper, and we neglected the conceptually simple case.
And then they add, hard to see due to the many algebraic cancellations.
Right, we were looking for something deeper. That sentence is literally a mirror held up to the scientific method.
It is the ultimate human blind spot. They were looking for poetry.
Exactly. They were looking for a profound, elegant, conceptual relationship that would make all the math beautifully, intuitively sing.
But the universe doesn't always write poetry. Sometimes the universe just writes a really messy, chaotic series of algebraic cancellations.
The human mind is incredibly powerful, but our aesthetic preferences can really become our prison, can't they?
They absolutely can. We get tired, we get bored, or we feel we are on the wrong path when things become ugly or overly reliant on brute force algebra.
We want the shortcut.
We do. But the AI didn't have that aesthetic bias. It didn't care if the path was uninteresting or tangled. It just relentlessly trudged through the mess that the humans deemed too ugly to explore.
It didn't care about being profound. It only cared about executing the logic correctly.
Exactly.
Which leaves us with a pretty provocative thought to mull over. If a team of Nobel-level physicists can get stuck for 10 years because they were overcomplicating a problem.
Looking for a profound answer when a simple one was right there.
Exactly. Looking for a poetic answer when a conceptually simple, albeit messy answer was sitting right there hidden in the algebra. How often do we do that in our own lives?
Oh, constantly.
We constantly want our problems to have deep, meaningful solutions. But sometimes the solution is just sitting down and doing the messy, tedious work.
Just pushing through the algebra of life, so to speak. And on a broader scale, for the future of scientific discovery, it raises an incredible question. If artificial intelligence doesn't care about our human concepts of mathematical elegance, what other scientific truths are currently hiding in plain sight?
Oh, that's a wild thought.
Right. What other universal laws are just waiting to be discovered purely because an AI is willing to brute force its way through the messy algebra that human intuition has walked past for decades?
It suggests that the future of discovery might not just be about seeing further into the unknown. It might be about being willing to look closer at the mess we've already discarded.
I couldn't have said it better myself. The beauty really is in the mess.
So the next time you find yourself stuck in a traffic jam or struggling to pack that final item into a cardboard box, remember, you aren't just annoyed.
No, you are participating in a universal, infinite-dimensional physics phenomenon.
And you don't always need a profound reason to get unstuck. Sometimes you just have to do the messy math. We will see you next time. Heliox is produced by Michelle Brucker and Scott Bleakley. It features reviews of emerging research and ideas from leading thinkers, curated under their creative direction with AI assistance for voice, imagery, and composition. Systemic voices and illustrative images of people are representative tools, not depictions of specific individuals. Thanks for listening today. 4 recurring narratives underlie every episode: boundary dissolution, adaptive complexity, embodied knowledge, and quantum-like uncertainty. These aren't just philosophical musings, but frameworks for understanding our modern world. We hope you continue exploring our other episodes, responding to the content, and checking out our related articles at helioxpodcast.substack.com.